So now that we've gone through drawing Lewis dot structures and for both simple molecules and some molecules that have a little bit more advanced aspects of Lewis dot structures, now we're starting to look at the length and strength of these bonds themselves. So this table that you have in front of you shows you just a sample of some covalent bonds, their bond dissociation energy, and their bond length. So what are those two things? What does that mean? We will go back to that table in a moment. But bond length is the average length between two atoms that are covalently bonded. The reason why it's just average is because in different molecules, the bonding and the length that is between a carbon and oxygen atom may be different. So we just take the average of all of the molecules. Same thing with bond energy. Bond energy is again the average. It's the average energy needed to break that bond, or the energy that's released when that bond is formed. So it can have sort of two meanings. So if I go back up to this data table here and I take a look at, let's say, carbon and oxygen. Carbon and oxygen make a single bond or a double bond or a triple bond. And let's look and see if we can find any patterns in between them. And if I look at single, double, triple, I'll notice something that the energy goes up. The energy goes up quite a bit from a single bond to a double bond to a triple bond. And that actually makes sense when I think of what a triple bond is. Remember, a triple bond is sharing 6 electrons. In order for the orbital overlap to be such that 6 electrons are shared, those atoms are, first of all, going to be, as we can see here, very close together. Their bond length is quite small, but then also it's going to take a lot of energy to overcome that bond, to overcome the attraction that each of those electrons feel for the opposite nucleus. So that's why triple bonds will always be shorter and stronger than single bonds. So the more bonds that you have when you go from double, single to double to triple, as you go through there, they get shorter and stronger. And why this is really important is because of how we're going to use bond energy. You know that in previous classes, you've talked about chemical reactions. And even in this class at the beginning of the year, when we think about a chemical reaction, we think about the idea that the bonds are broken and new bonds are formed. When every chemical reaction that happens, those two processes take place. In every chemical reaction, bonds are broken and new bonds are formed. And energy needs to be added to break bonds, because those, what is a bond? It's the attraction between electrons and a nucleus. So if we need to break that bond, we need to overcome that attraction. That's always going to take energy. And the exact opposite is true. Energy is released when new bonds are formed. Because when new bonds are formed, we're taking atoms that don't have a full octet and now they have a full octet. They're in a much more stable state, so they have less energy. So how do they get less energy? They release that energy. So that means in every chemical reaction, you got to put some energy in and some energy out. Well, depending on which one is larger, we can then define this reaction as endothermic or exothermic. And you've heard those terms before in previous classes. If the sum of all these energies, so the amount of energy in is positive, the energy out would be negative. If the sum of those energies is positive, that means overall we've added energy into the reaction. Energy was absorbed, and we call that reaction endothermic. And the exact opposite is also true. If the sum of these energies is negative, which means I put in a positive amount of energy and I got out a much larger negative amount of energy, right? I subtracted a large amount of energy, then my answer would overall be negative, and overall energy was released, and the reaction is what we call exothermic. And so in every chemical reaction, we can figure out what were the bonds that were formed, what were the bonds that were broken, and add those up to figure out whether the reaction is endothermic or exothermic. So if we look at this graphic right here, you can see here are the reactants. The reactants in this case are a molecule of hydrogen gas and a molecule of chlorine gas. So the first thing that happens is energy is added. You can see energy is needed to break the chlorine-chlorine bond, this amount of energy specifically. And 432 kilojoules per mole is needed to break the hydrogen-hydrogen bond. So now look what we have. We have these 4 atoms, right? We've taken the molecules, we've broken apart all the bonds, we've broken apart all the bonds, and now we have the loose atoms. And we can see that they will, in fact, rearrange, right, to make the products. Here are the new products. A hydrogen is bonded with a chlorine, and that has happened twice because those atoms have come and now those atoms have a full octet. Energy is released, and we can actually figure out how much energy is released. And then when I add up, right, I add energy that I put in to break the bonds, and then the energy released, see how that number is negative? The energy released when those new bonds are formed, I get a negative number. That tells me that this reaction was exothermic. So what we're going to do is we're going to basically do this for a bunch of chemical reactions here. So the formula for this, and this would be to find delta H. What is delta H? That is the energy change in a reaction. It could be also called enthalpy change. There's a little difference between energy and enthalpy that we go into in AP chemistry. For our purposes, they can be pretty much synonymous. And this symbol right here, the Greek letter sigma, means sum. So the sum of the bonds broken, which would be in the reactants, minus the sum of the bonds formed. And this is the chemical reaction we're going to use. So the first thing that we're going to need to do is actually write Lewis dot structures for these molecules. So hydrogen and hydrogen, of course, you know, if I'm writing the Lewis dot structure for H2, there's just 2 electrons, so it's just 1 bond. See how there's a coefficient of 2 here? That means that there's 2 of them, and I like to write both of them in there just because sometimes I may forget how many bonds there are. O2, oxygen, has 12 valence electrons, so I would use 2, so I'd have 10 left over. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That oxygen doesn't have a full octet, so a double bond. And there's only 1 of those, so I'm only going to draw 1 of those, right? And then water. Water has 8 valence electrons. I use 2 to make the bonds. That gives me, I use 4 to make the bonds. That means I have 4 left over and they go on the central atom. And again, because there's a coefficient of 2, I'm going to draw that molecule twice. Now, I go for the sum of the bonds broken. So that would be 2 times a hydrogen-hydrogen single bond and 1 times an oxygen-oxygen double bond, right? This would be the sum of the bonds broken minus the sum of the bonds formed would be 4 times an oxygen-hydrogen single bond. We need to be careful because single bonds and double bonds and triple bonds are going to have different numbers. So now I can use the data on the data table 8.4 to help us out. Hydrogen is right here, 436. plus oxygen, and oxygen is 495 kilojoules per mole, minus 4 times oxygen and hydrogen is 463. Okay, so I looked on the table and I substituted in the values, then I multiplied. So the total bonds broken is this 1367 number, kilojoules per mole. The total bonds made was 1852, right? It's bonds broken minus bonds formed. So when I do the subtraction there, I get a negative number, negative 485 kilojoules per mole. What that means is the negative doesn't mean less than 0. The negative tells me that the reaction is losing energy. So that means 485 kilojoules of energy is released when this reaction happens, when a mole of this reaction happens. So what that means is it is related to this chemical equation by its coefficients. When 2 moles of hydrogen react with 1 mole of oxygen and produce 2 moles of water, 485 kilojoules of energy will also be released. That means that this reaction, because delta H turned out to be a negative number, this reaction is exothermic. The energy that went in to break the bonds is less than the energy released when those new bonds are formed.